All right, good morning, guys. We are the Privacy Leakage Study and Protection for Virtual Reality Devices. I am Dirk. I'm a master's student here at Rutgers under the ECE department.
I'm Brody. I'm a rising freshman at the Rutgers ECE department.
I'm Emily. I'm a rising senior at High Technology High School.
And here are also our mentors, Chaiming Honglu Tianfeng, and our advisor, Professor Ying Jennifer Chen, which helped us out throughout this project as well. So the motivation why we pursue this project is because these AR, VR devices have attracted millions of users throughout the years, and they're used in many different applications as gaming, shopping, banking, education. And between all these devices, they all share a key component, which is the inertial measurement unit, which just means IMU or short for IMU, which consists of the accelerometer for acceleration and gyroscope for the rotations. And both these sensors are present in all these devices. So the headset will have these two sensors and a left controller and right controller as well. And these sensors are also known as zero permission sensors, which means that they're constantly on whether you like it or not. And that's because these devices need these sensors to actually do certain rotations and certain movements inside different games and applications. And yeah, this project aims to study the sensor data management in commercial AR/VR headsets and analyze the potential of private information leakage. And as I mentioned before, we're investigating the privacy leakage. And to do this, what we first do is extract the data from the IMU and then see if it was able to do any human activity recognition with different motions that we'll show later on. And also use a support vector machine and large language model to show how the IMU data maliciously exposes activities of victims or the users. And as an attack illustration, we are using the SVM as a baseline. So we could find the statistical features and then input those statistical features inside the LLM to improve the accuracy of the LLM, as I mentioned right here as well. And then if the LLM and the SVM the accuracy are pretty similar, we'll able to say that the LLM validates the adversaries could expose victims' motion status without requiring lots of data from the victims. And here is a quick block diagram of how we go from start to finish in this project, in which we collect the motion data, pre-process it, input into the SVM, construct the LLM prompt based on the statistical features that are best for that, and input this into the LLM. Then we compare the results of the SVM and LLM as well. And to make sure that the motions that we're getting or the IMU data we're getting corresponds with a certain motion that we're doing, we use MATLAB to make certain waveforms and also 3D graphs. And in this example, we're doing a side raise, which is a simple side raise like this. And this right here is the z-axis accelerometer, which corresponds to the motion we did do in the z-axis and acceleration meters per second squared. And over here is the 3D graph, in which on the right-hand side, we have a color bar, which a dark blue corresponds to 0 seconds and a dark red corresponds to 6 seconds. And if you were to follow this line right here, it starts in the middle as a dark blue, which is just your hand stationary. And you'll follow the motion throughout the time. You'll see that it does correspond to that motion that we did, which was the side raise.
So for the SVM, the most important features that we wanted to extract were the mean peak to peak and the interquartile range. So here you see we're doing the same movement 3 times. The graphs and the values for the statistical features were very similar. For the gyroscope graph, we did the same statistical analysis, and we are analyzing 3 different movements here. And you can see how the graphs and the statistical values are very different and distinct.
So this is an explanation of what a support vector machine actually is and does. And it's an effective machine learning algorithm that is used for classification. So what it does is it basically takes features and puts them on points in a plane, and it creates a hyperplane that differentiates the 2 classifications. And then it takes a huge amount of data for this classification, as it needs a lot of points to create an effective hyperplane, as it maximizes the margin between the 2 clusters of points.
So this is the large language model, LLM, and it works well on recognizing human language, and it could also do other complex tasks. It could also understand data and give you the desired outputs depending on your prompt. And unlike the SVM, it's pre-trained on vast amounts of data, and attackers won't need to get training data from their victim users, and that means they could accurately expose human motions without that. So if the LLM can get similar results to SVM without training, that means an attack will be feasible with LLM.
So this is our experiment setup using Android Studio and MATLAB. We were able to write out this little code here, which would actively take the sensor outputs from the accelerometer and gyroscope in each controller and the headset. So as you can see here, we created 6 activities for evaluation, including 2 arm-related movements and 4 head-related movements. So you can see here. And so this was the activity inference using the SVM. So we took the 3 statistical features, the mean, the peak-to-peak, and the interquartile range, and we created a confusion matrix here that represents the overall accuracy. So this is where our true labels are, and this is where the predicted labels are. And as you can see, we had a very high accuracy overall, 99.33%.
For the LLM, we developed a prompt for Gemini Advanced to understand our motion data. We basically explained the goal of our task and what type of data it's going to be receiving. We also asked the LLM to extract certain features and had it analyze it in specific ways. And we also had it, we also gave a structure of how we wanted a response to look like. So this is an example of us giving us how we wanted to interpret the data based on the features that it extracted. So using our prompt, we basically put that into Gemini Advanced along with the CSV files. And we would read the response that it would give us. And from there, we determine whether or not the response was accurate based on how many sensors it was able to get accurately. So here you can see we ended with a 90.6% accuracy. So with our current prompt that we designed, the LLM achieves an accuracy similar to the SVM, indicating the potential activity information leakage without the training effort like the SVM. With further prompt tuning, adversaries could realize a stronger activity exposure attack using LLM. Thank you for your time. Any questions?